This study delves into the generalization capabilities of YOLOv8 and YOLOv9 models for cow detection in indoor freestall barn settings, focusing on varying training data characteristics such as view angles and lighting, and model complexities. Utilizing the newly released public dataset, Cow's Localization (COLO) dataset, the research investigates three key hypotheses. 1. Model generalization is equally influenced by changes in lighting conditions and camera angles. 2. Higher model complexity guarantees better generalization performance. 3. Fine-tuning with custom initial weights trained on relevant tasks always brings advantages to detection tasks. The findings reveal considerable challenges in detecting cows in images taken from side views and underscore the importance of including diverse camera angles in building a detection model. Furthermore, the results emphasize that higher model complexity does not necessarily lead to better performance. The optimal model configuration heavily depends on the specific task and dataset, highlighting the need for careful model selection tailored to the particular application. While fine-tuning with custom initial weights trained on relevant tasks offers advantages to detection tasks, simpler models do not benefit similarly from this approach. It is more efficient to train a simple model with pre-trained weights without relying on prior relevant information, which can require intensive labor efforts. Future work should focus on adaptive methods and advanced data augmentation to improve generalization and robustness. This study provides practical guidelines for PLF researchers on deploying computer vision models from existing studies, highlights generalization issues, and contributes the COLO dataset containing 1254 images and 11,818 cow instances for further research. Object localization is a crucial aspect of precision livestock farming, where accurate detection and tracking of animals enable informed decision-making. Computer vision techniques, including object detection, segmentation, and pose estimation, have been increasingly applied in farm settings. Models such as YOLO, Faster RCNN, and SSD have demonstrated effectiveness in detecting animals, while Mask RCNN and UNet have been employed for object segmentation. However, deploying pre-trained models in new environments often results in poor performance due to factors like camera angles and lighting conditions. This discrepancy highlights the need for model generalization. Fine-tuning is a common practice to alleviate this issue, allowing models to adapt to new environments. This study investigates the generalization capabilities of these models using the COLO dataset, which comprises images of cows in various environments and poses. The COLO dataset provides a comprehensive evaluation framework for assessing the robustness of object localization models in real-world farm settings. The study's findings emphasize the importance of fine-tuning pre-trained models to achieve optimal performance in new environments. The results also highlight the limitations of current models in handling variations in camera angles and lighting conditions. Future work should focus on developing more robust models that can generalize across diverse environments and conditions. The COLO dataset offers a valuable resource for researchers to evaluate and improve the performance of object localization models in precision livestock farming. By exploring the generalization capabilities of these models, this study contributes to the development of more accurate and reliable computer vision systems for farm animal monitoring. In the realm of computer vision, deploying models for real-world applications poses significant challenges, particularly concerning model generalization and complexity. Fine-tuning pre-trained models on new datasets can enhance their generalization capabilities, but success is not guaranteed. It largely depends on the quantity and quality of the annotated dataset. Model complexity also plays a crucial role, as it affects both generalization performance and computational cost. The study introduces YOLO models as an efficient approach to object detection, capable of performing the task in a single pass through the network. Specifically, YOLOv8 is discussed, which builds upon the YOLOv5 architecture and incorporates the C2F module for enhanced performance. The C2F module features two convolutional operations and uses COLO activation for smoother gradient flow. The paper concludes by highlighting the trade-off between model complexity and computational cost, a critical factor to consider when deploying CV models in real-world scenarios. This trade-off is essential for achieving optimal performance while minimizing computational resources. This study delves into the generalization capabilities of YOLO family models in varying environmental settings and model complexities for indoor cow localization. It commences with object detection as a baseline task, aiming to understand model behavior and performance before extending to more complex tasks such as segmentation and posture estimation. The YOLO family models, including YOLOv8 and YOLOv9, are chosen due to their anchor-free approach and ability to predict bounding boxes and confidence scores directly, simplifying the network and reducing computational overhead. YOLOv9, in particular, addresses the information bottleneck issue through innovations like programmable gradient information (PGI) and the Generalized Efficient Layer Aggregation Network (GELAN). PGI optimizes gradient generation to minimize deep layer information loss, featuring a main branch for inference and auxiliary branches for enhanced training. GELAN ensures robust feature retention by integrating and pooling convolutional layers, notably boosting inference speed by 20% on the COLO dataset while facilitating the detection of objects across varying sizes. Public datasets play a crucial role in the development of methodology based on the same baseline. For instance, the ImageNet dataset serves as a benchmark for image classification, accelerating the development of CV models. However, a generic public dataset may not be sufficient for specific use cases like livestock scenarios. Efforts have been made to create public datasets for livestock applications, such as the Cattle iView dataset, the Pig dataset, and the Open Cows 2020 dataset, which support various applications including cattle pose estimation, behavior analysis, and precision farming. This study aims to use YOLO family models to explore model generalization across varying environmental settings and model complexities within the context of indoor cow localization. The study examines three hypotheses. 1. YOLO family models can effectively detect cows in indoor environments with varying lighting conditions. 2. Model complexity affects the performance of cow detection. And 3. The use of transfer learning can improve model performance in detecting cows. Computer vision models have shown promise in various applications, including cow localization tasks. However, their generalization capabilities under varying conditions remain a concern. This study investigates the impact of lighting conditions and camera angles on the performance of computer vision models in cow localization, shedding light on the factors that influence model generalization. The results indicate that both lighting conditions and camera angles equally affect model generalization, with higher model complexity leading to better performance. Notably, fine-tuned models consistently outperform pre-trained models, particularly when the deployment environment differs from the training environment. This suggests that fine-tuning can adapt models to new environments, enhancing their generalization capabilities. To facilitate further research, a new dataset, Cows Localization (COLO), will be developed and made available to the community. This dataset will enable researchers to investigate the effects of various factors on model generalization and develop more robust computer vision models for cow localization tasks. The study's findings have practical implications for precision livestock farming researchers deploying computer vision models. By considering available resources and anticipated performance, researchers can make informed decisions about model selection and fine-tuning, ultimately improving the accuracy and reliability of cow localization systems. The results of this study provide valuable insights into the factors that influence model generalization, paving the way for the development of more robust and adaptable computer vision models. The COLO dataset is a comprehensive collection of images for cow detection and counting, comprising 1,200 images from 3 different camera angles: top view, side view, and external. These images were captured under various lighting conditions, including daylight, indoor, and near-infrared. The dataset includes 113 images taken in the evening and 97 near-infrared images from the side view camera, while all images from the external camera were captured during the day. Each image has been annotated using an online platform, RoboFlow, to define cow positions. Bounding boxes were manually drawn to enclose the cow contours, providing coordinates of the top left corners and the width and height of the boxes. If cows were partially occluded, the invisible parts were inferred based on the adjacent visible parts. If the cow position was too far from the camera, making important body features unrecognizable. The cow was excluded from the dataset. The final annotations were saved in the YOLO format, where annotations were stored in a text file with one row per cow in the image. This dataset aims to provide a robust foundation for model generalization studies in cow detection and counting tasks, particularly under diverse environmental conditions. The study presents a model generalization analysis using the COLO dataset, focusing on object detection models for cow identification in various environmental conditions. The model training was conducted with default hyperparameters and data augmentation techniques to enhance generalization. The evaluation metrics include precision, recall, mean average precision, MAP, at an IOU threshold of 0.5, and averaged MAP at varying IOU thresholds from 0.5 to 0.95. The cross-validation strategy involved 5 training configurations: baseline, top to side to top, day to night, and external. Each configuration aimed to assess the performance drop when models were trained on one dataset configuration and tested on another. This approach helps in understanding how well the models generalize across different view angles and lighting conditions. The results of this study can provide insights into the effectiveness of object detection models in real-world applications, particularly in scenarios where data collection is limited or diverse. By evaluating the model's ability to generalize, researchers and practitioners can better understand the strengths and limitations of these models and develop strategies to improve their performance in various environments. This study explores the generalization capabilities of object detection models using the COLO dataset. Researchers employed a cross-validation approach, splitting the dataset into 5 configurations: baseline, top to side to top, day to night, and external. Each configuration was evaluated with varying training sample sizes, ranging from 16 to 512 images, with the testing set fixed at 100 images. The training sample size was doubled at each step, and each size was repeated 50 times with different random seeds to ensure robust results. The study utilized the YOLOv9 model, the most capable in the YOLO family, as the base model. Researchers also examined the correlation between model complexity and performance on the task of localizing cows. 5 YOLO family models were evaluated: YOLOv8n, YOLOv8 meters, YOLOv8x, YOLOv9c, and YOLOv9e. The YOLOv8 models share a similar architecture, differing in their depth multiplier, width multiplier, and ratio factor, which determine their parameter counts. The YOLOv8 models have parameter counts of 3.2 million, 25.9 million, and 68.2 million, respectively. The depth multiplier determines the number of convolutional layers in a C2F module, while the width multiplier and ratio factor specify the channel numbers in convolutional operations. The YOLOv9c and YOLOv9e models have parameter counts of 25.6 million and 58.2 million, respectively, with slightly different backbone architectures. YOLOv9c has 618 layers and uses simpler modules, resulting in a more efficient model, while YOLOv9e has 1225 layers and employs more advanced modules. The study aims to investigate whether model performance increases with model complexity. The researchers evaluated the models on the COLO dataset, examining the impact of training sample size on model performance. The results will provide insights into the relationship between model complexity and performance on the task of localizing cows. This study delves into the generalization capabilities of various object detection models using the COLO dataset. The COLO dataset, publicly available on GitHub and Hugging Face platforms, comprises 1254 images and 11,818 cow instances captured from an indoor farm environment. It is organized in YOLO and COCO formats and consists of 8 configurations, including baseline, top view, side view, external, and cross-view scenarios. The study evaluates the performance of 5 object detection models: YOLOv8n, YOLOv8 meters, YOLOv8x, YOLOv9c, and YOLOv9e by training them on 500 images in 5 cross-validation configurations: baseline, top to side to top, day to night, and external. The model's performance is assessed using mean average precision at intersection over union thresholds from 0.5 to 0.95. Additionally, the computing speed of each model is evaluated, including training speed in seconds per 100 epochs on NVIDIA A100 GPUs and inference time in frames per second on both CPU and GPU. The relationship between model complexity and time consumption is analyzed to provide insights into the trade-off between model performance and computational cost. Furthermore, the study assesses the advantages of using fine-tuned model weights over pre-trained model weights as initial model weights. The fine-tuning configurations are described in Table 1, with different initial weights obtained from the pre-trained model on the COLO dataset and the fine-tuned model on the opposite view angle. The backbones of all models are fine-tuned across different training sample sizes: 16, 32, 64, 128, 256, and 500. The goal is to determine whether the advantage of using fine-tuned weights persists under the interaction between model complexity and different fine-tuning samples. The performance of the models is evaluated using mean average precision at intersection over union thresholds from 0.5 to 0.95. The study delves into the generalization capabilities of YOLO models trained on the COLO dataset, focusing on the impact of camera view angles and environmental conditions. The COLO dataset is a collection of images taken from various angles and under different lighting conditions, providing a comprehensive platform for model evaluation. The Hugging Face version of the dataset offers additional functionality to resize images and annotations to specific resolutions, enhancing flexibility for various applications. The evaluation metrics used in this study include precision, recall, and two variants of the average precision (AP) metric. These metrics provide insights into both the localization and classification capabilities of the models, helping to identify strengths and weaknesses under different environmental conditions and camera angles. The AP metric is the most stringent, requiring high positioning accuracy and high precision across IOU thresholds from 0.5 to 0.95. Achieving an AP greater than 0.90 is generally unrealistic. Typically, a value of 0.7 is considered good and is sufficient to yield precision and recall of around 0.9. In contrast, AP 50 is more lenient, requiring high confidence but only moderate IOU. It measures the average precision at an IOU threshold of 0.5. For applications where counting cows is more important than precise positioning, an AP 50 value of 0.9 is sufficient. For example, the YOLOv8 model, trained on 32 samples, achieved an AP 50 of 0.9, making it suitable for such applications. Precision and recall metrics focus on the accuracy and completeness of the detections. Precision is the ratio of true positive detections to the total number of positive detections, true positives plus false positives, measuring how accurate the positive predictions are. Recall is the ratio of true positive detections to the total number of actual positives, true positives plus false negatives, measuring the model's ability to detect all relevant objects. Generally, higher precision is associated with higher recall. However, in some configurations, such as side to top and external with smaller sample sizes, models exhibited high recall but low precision. This indicates a tendency to misclassify non-cow objects as cows more frequently than missing actual cows, suggesting a tendency to overestimate rather than underestimate the number of cows in the images. The study emphasizes that for applications where counting cows is more critical than precise positioning, achieving a high AP 50 is adequate, while the stringent AP metric serves as a comprehensive indicator of overall model performance. These metrics provide insights into both the localization and classification capabilities of the models, helping to identify strengths and weaknesses under different environmental conditions and camera angles. The study on model generalization using the COLO dataset presents a comparative analysis of model performance under various data configurations. Changes in camera views, specifically from top to side and side to top, resulted in a significant performance drop of approximately 30% and 60% respectively. In contrast, changes in lighting conditions, such as day to night, did not dramatically affect model performance across all four metrics. From the perspective of precision and recall, the top two-side configuration consistently showed the worst performance, with the model missing more than 7 out of every 10 cows and only 50% of the detections being correct. The external configuration identified 6 out of every 10 cows, which is not ideal but not the worst performance observed. Notably, performance in the day-to-night configuration was close to the baseline in terms of precision, indicating that changes in lighting conditions did not affect model performance when excluding low-confidence predictions. The study also highlights that model performance always increased as the training sample sizes increased, regardless of the configuration and evaluation metrics. This comparative analysis provides insights into the behavior of the model in various data configurations, showing that the day-to-night configuration exhibits much better performance relative to the heterogeneous viewpoint-oriented configurations, top-to-side, and side-to-top. The study examines the generalization performance of YOLOv9 across various data configurations and training sample sizes using the COLO dataset. Figure 4 illustrates the model's performance in terms of precision and recall for different training samples and data configurations. Notably, the day-to-night configuration maintains high precision, closely mirroring the baseline configuration across all training sample sizes, indicating that changes in lighting have less impact on object detection compared to changes in viewpoint. The inclusion of diverse lighting conditions in the training phase, combined with pixel-wise augmentation techniques such as adjustments to hue, saturation, and value, HSV, enhances the model's ability to generalize across different visual conditions. However, the models perform suboptimally in scenarios involving changes in viewpoint, as each new viewpoint introduces fundamentally different object features that are not replicated through standard data augmentation methods. For instance, when the camera is placed at a lower angle, cows are more frequently occluded by stalls and fences, introducing variations that cannot be mitigated by augmentations in HSV space or image translation. The top-to-side configuration performs the worst, as identifying cows from the side is particularly challenging. Even for the external configuration, the model struggles to generalize well despite being trained on the baseline configuration, due to the changed camera angle. These findings highlight the importance of considering diverse viewpoints and lighting conditions during model training to enhance its adaptability and robustness. Camera view angle is crucial for model generalization, with side views being the most challenging. The study underscores the need for more comprehensive training data that accounts for various visual conditions to improve the model's performance in real-world applications. The study delves into the relationship between model complexity and performance in object detection tasks, leveraging the COLO dataset. It reveals that augmenting model complexity does not necessarily translate to enhanced generalization, as simpler models often outperform their more complex counterparts in certain configurations. YOLOv8 and YOLOv9 models are assessed across a spectrum of model parameters and data configurations, yielding results that indicate different model architectures exhibit distinct performance trends with varying complexities. YOLOv8 family models tend to excel with mid-sized models, whereas larger models in the YOLOv9 family generally perform better. The research concludes that model performance is determined by both the training configuration and the model architecture. This underscores the importance of understanding the interplay between these factors to optimize object detection tasks. This study delves into the generalization of YOLO models in detecting cows within an indoor farm setting, utilizing the COLO dataset. It reveals that higher model complexity does not necessarily translate to better performance, as the optimal model configuration is heavily dependent on the specific task and dataset. The findings suggest that a small model such as YOLOv8n, with only 3.2 m parameters, can achieve 90% accuracy with a relatively small size of training samples, emphasizing the importance of considering the specific characteristics of the task and dataset when choosing a model. Additionally, the study reveals that the benefit of using fine-tuned initial weights is minimal for simpler models. For YOLO models with fewer parameters, such as YOLOv8n and YOLOv8 meters, the choice of weight initialization does not make a significant difference in fine-tuning performance. However, larger models like YOLOv8x, YOLOv9c, and YOLOv9e exhibit improved performance when weights are initialized from a model that has been previously fine-tuned in a similar data configuration. The analysis also provides insight into performance across homogeneous viewpoint data configurations, specifically top-view camera and side-view camera. The data demonstrates that the top-view camera configuration consistently yields higher map values regardless of the training sample size and weight initialization conditions, indicating that the side-view camera configuration presents a more formidable challenge for cow detection compared to the top-view camera configuration. This study delves into the generalization performance of YOLO models across different datasets, with a particular focus on the impact of initial weights and training samples. The findings suggest that fine-tuning with custom initial weights trained on relevant tasks can significantly enhance detection performance, especially for complex models. However, simpler models do not benefit much from customized weights, indicating it is more efficient to train them with pre-trained weights. The study also underscores the importance of considering computational resource requirements when deploying YOLO models in real-world applications. The evaluation reveals that larger models, such as YOLOv8x, require more training time and have slower inference frames compared to smaller models like YOLOv8n. This information is crucial for understanding the feasibility of deploying these models in environments with limited computational resources. In conclusion, this research emphasizes the need for careful consideration of model complexity, initial weights, and computational resource requirements when applying YOLO models to various datasets. By understanding these factors, researchers and practitioners can optimize their object detection tasks and improve overall performance. This study assesses the generalization capabilities of YOLO models using the COLO dataset, focusing on computational resource requirements. It compares YOLOv8 and YOLOv9 models in terms of training time, inference frequency, and model weight sizes. The results indicate that as the number of parameters increases, so does the training time for both YOLOv8 and YOLOv9 models. However, YOLOv9 models demonstrate a more significant increase in training time compared to YOLOv8 models, especially when the number of training samples is large. Inference time was measured as the average frames per second, FPS, in a batch of 64 images. The findings show that running the models on a CPU with the smallest model, YOLOv8n, was slower than running the largest model, YOLOv8x, on a GPU. High FPS models are essential for real-time inference, which usually requires a model with an FPS higher than 30. The results indicate that implementing YOLO models on a CPU may not meet real-time requirements, especially for larger models. Model weight sizes were also considered, impacting memory requirements and deployment feasibility, especially in edge computing environments. The weight sizes and parameter counts of various YOLO models are displayed in Figure 7c. In conclusion, this evaluation highlights the trade-offs between model complexity and computational efficiency. The larger YOLO models, while offering potentially better performance, require significantly more computational resources. This analysis helps researchers and practitioners select the appropriate model based on the available computational resources and the specific requirements of their application. This study delves into the impact of various training configurations and model complexities on the performance of YOLOv8 and YOLOv9 models for cow detection in indoor farm environments. The findings reveal that model performance is highly dependent on camera viewpoints, with side views presenting the greatest challenges. Fine-tuning models with weights from similar datasets significantly enhances performance, particularly for complex models in scenarios with limited data. The study also introduces a public cow localization dataset, COLO, to support the research community. The results suggest that while increasing model complexity can improve performance, this is not always the case, especially in challenging configurations like top-to-side, which predict images from a side view using a model trained on top-view images. Models trained on a single viewpoint exhibit limited generalization, underscoring the importance of incorporating diverse and consistent camera angles in the training data. Despite the promising results, this study has certain limitations. The model's performance was evaluated under specific indoor farm conditions, which may not generalize to all livestock environments. Moreover, the reliance on predefined configurations may limit the applicability of our findings to more dynamic settings. Future work should explore adaptive methods for enhancing model generalization across varied viewpoints and environmental conditions. Additionally, investigating the integration of advanced data augmentation techniques and more diverse datasets could further improve detection accuracy and robustness. In conclusion, This study offers practical insights into reproducing model performance in new environmental settings and provides the public COLO dataset to facilitate further research and advancements in the field. This research paper presents a comprehensive study on model generalization using the COLO dataset. The authors have provided an extensive list of models and their performance metrics, which are crucial for understanding the effectiveness of different approaches in this field. The COLO dataset is a collection of images that are used to evaluate the generalization capabilities of various machine learning models. It consists of images from different domains, such as animals, vehicles, and objects, which allows researchers to assess how well models can adapt to new data distributions. The paper discusses several key findings related to model generalization. Firstly, it highlights the importance of domain adaptation techniques in improving model performance on unseen data. Secondly, it shows that models trained on large datasets tend to perform better than those trained on smaller datasets, even when tested on out-of-domain data. Furthermore, the authors explore the role of model complexity in generalization. They find that simpler models often perform as well as or better than more complex models, suggesting that overfitting may be a significant issue in some cases. In conclusion, this study provides valuable insights into the factors that influence model generalization and offers practical recommendations for improving model performance across different domains. In the realm of machine learning and computer vision, model generalization is a crucial aspect that researchers continuously strive to improve. A recent study utilizing the COLO dataset has shed light on the performance of the YOLOv8 model, developed by Ultralytics, in terms of its generalization capabilities. The YOLOv8 model, an iteration of the YOLO family, is a real-time object detection system that has garnered significant attention due to its balance between speed and accuracy. The COLO dataset, comprising images from various domains such as animals, vehicles, and everyday objects, provides a diverse platform for evaluating the model's generalization capabilities. The study reveals that the YOLOv8 model demonstrates robust performance across different domains, showcasing its ability to adapt and learn from diverse data. This is attributed to its architecture, which incorporates several key features including spatial pyramid pooling, cross-stage partial connections, and multiscale training. Furthermore, the research highlights the importance of data augmentation techniques in enhancing the model's generalization capabilities. By applying various augmentations such as rotation, flipping, and scaling, the model can learn to recognize objects under different conditions, thereby improving its performance on unseen data. While the study showcases the YOLOv8 model's impressive generalization capabilities, it also identifies potential areas for improvement. For instance, the model's performance can be further enhanced by incorporating additional domain-specific data or fine-tuning the model on specific tasks. In conclusion, the study on the YOLOv8 model using the COLO dataset underscores the significance of model generalization in computer vision tasks. It emphasizes the need for continuous research and development in this area to create more robust and adaptable models that can perform well across diverse domains and conditions. The paper delves into the realm of machine learning and computer vision, focusing on object detection models, their variants, and applications in different domains. It begins by referencing the YOLO model for unified, real-time object detection, which has been influential in the field of computer vision. The authors also mention RoboFlow, a platform designed to organize, annotate, and improve machine learning datasets. The discussion then shifts to UNet and its variants for medical image segmentation, highlighting their theory and applications. This is complemented by a reference to the concept of very deep convolutional networks for large-scale image recognition, as proposed by Simonian and Zisserman. The ResNet architecture is also discussed, which generalizes residual architectures. The FCOS model for fully convolutional one-stage object detection is further explored, along with the information bottleneck principle and its application in deep learning. The authors also touch upon the automatic detection and segmentation of group-housed livestock using keypoint detection and map estimation. An overview of various YOLO models, including YOLOv8, and their documentation is provided. This comprehensive analysis aims to bridge the gap between complex research papers and concise, informative summaries for expert audiences. In the appendix of this study, The hyperparameters used in the Ultralytics library for training the models are detailed. These parameters include the number of training epochs, batch size, optimizer, and various image augmentation techniques such as altering hue, saturation, brightness, translation, scaling, flipping, mosaic creation, mix-up, and copy-paste. The values for these hyperparameters are provided in Table 3, showcasing the specific settings employed during the model generalization study with the COLO dataset. This information is crucial for understanding the training procedure and its implications on the model's performance and generalizability.